Welcome to this topic video on authentication and password management. So, authentication is the process of verifying that an individual entity or website or computer or IoT or whatever thing is who it claims to be. Okay. Authentication in the context of web is usually done by submitting a name or ID and one piece of private information or more, okay, like a password, okay, or some other mechanism. References, okay. I know it sounds like it's just a short little cheat sheet. This is actually a very good thing to read, okay. Defines authentication, relates it to password management. Password storage cheat sheet. Before you do a real deployment, make sure you read this. Okay. Some of the greatest and latest techniques as of 2018 are gone through in this nice piece of blog post. Now, we are going to, in this class, concentrate on password-based authentication. There are other forms, okay, out of our scope here. Common attacks against passwords. Brute force. The password is too short. Guessing attacks. The password is too common. Credential stuffing. The password has been exposed in other breaches. So what can you do? Countering these attacks. Password length. Okay. We can require users of our website have a length that is given a certain meets certain minimum criteria, and we can even check that the password has a certain amount of content requirements. Okay. If you want to go further, we can check against common passwords. It's a little bit more work, but not impossible. Okay. Credential stuffing. Okay. This one we can't do much about. We can tell and recommend users don't use the same password for two different sites. Okay, this is really important for users. Okay, see this credential stuffing prevention cheat sheet. Okay, bad passwords. Okay, there are lists over at GitHub. Okay, what do I mean? Let's go see. Of bad or commonly used passwords, okay? They have lists of them, common credentials, permutations, all these different things, okay? Security lists, passwords, okay? You can use those for security testing or for evil. There are people out there that'll use them for evil. The top 20 passwords, yeah. No mysteries. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. QWERTY, right? Across the top row of the keyboard. Okay? Why not just try them all? Easy to do. Okay? Password storage and theft. Issues. Passwords used for website app authorization, okay, authentication and authorization, need to be kept on the server. We don't have a choice. Okay? Many attacks focus on trying to get at these assets. Even for a large site with hundreds of millions of users, or billions of users, the entire password user database can fit on a moderate-sized memory stick, right? Hey, plug this USB stick in and give me a little bit of data, right? Just isn't that difficult, okay? That's considered an insider threat. How can you counter this? Oh, encryption and stuff. But it's more than that, and we're going to see. Users' passwords should never, ever, 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 ever be stored in the clear, meaning unencrypted, okay, on the server, or on the user's password, on the user's computer either, okay? Here's the catch. Most common encryption algorithms are designed to be very fast and efficient. This poses special problems for password storage, okay? These algorithms, like we use for HTTPS, okay, that are used, okay, are very fast. They have to be because we're sending lots of data back and forth. However, That causes a problem for password storage. Okay, why not try them all? If I give you a database of encrypted stolen passwords, couldn't I just try encrypting all 10 million of the most common passwords and looking for matches against the database? So I run the encryption algorithm once on all those 10 million most common passwords. I grab the stolen password library that somebody, database that somebody's handed me. They're encrypted. Okay. Yeah. Easy. Yes, encryption and hash algorithms are designed to be fast. So going through 10 million database items and encrypting each one of them and looking for a match is very feasible. This is known as a dictionary attack. Okay. One set of encryption, boom. Try all those matches against the thing in the database. Easy. We can make it a bit harder, though, by adding some salt. Huh? Okay. Like I said, they're going to attack the entire database at once. They're going to take the 10 million most common passwords, use the same encryption algorithm and encryption key that was used to encrypt that database, and they're going to look for matches. Okay? So they only have to do all that encryption once. What if they had to do it for each item? They had to go re-encrypt each of those 10 million passwords, okay, to try against each user's. Oh, so what we do to make it a little harder or a lot harder is we add some binary data, okay, to the password, okay. So here we have their password, we have this extra binary data, we got this protection function, okay, and such like that we're going to use. Professor, how do we know what the salt was? Oh, well, we store it with it. So it's not encrypted. No. So they can see it, but they still have to try all these different combinations against this entry. Okay. So you'll hear people talking about salting passwords. Very important. Okay. Most good algorithms that we're going to see have this as a key step in them. Okay. So this is the explanation. The attacker has to do more work for each entry. This doesn't help at all if it's a targeted attack against one particular user. Okay, that's a different story. Okay, but a lot of these attacks go for the easy ones. Okay, the user that uses a common password in that list of 10 million. Okay. Rules for the SALT. Okay, these come from the Open Web Application Security Project. Generate a unique SALT upon creation and storage of each credential. Okay. Use cryptographic, whatever does that mean? Cryptographically strong random data? Random data is random data. Why worry about it? We'll see. As storage permits, use a 32-byte or 64-byte SALT. Okay. Now, random numbers. On our computers, there are two very different types of random numbers used in computing, okay? And I've used them both. Those used in computer simulations, like for network simulations or for games, must be very, very fast. But let's really focus on simulations. Must be very fast, okay? They have to have a wide range of good statistical properties, okay? The sequences generated must be repeatable given the same seed. How are these random? They look very, very random, okay? Example, the Math.random function in JavaScript, okay? Looks very random, okay? However, it's completely predictable if you have enough information. Cryptographically random data, okay? These cannot be predictable in any way, okay? They usually are generated by performing some cryptographic operating systems on some natural sources of randomness, okay? Node.js has this crypto.randomBytes function, okay? We won't be using that directly, but methods, functions that we will be using will. Okay, very different. This is more costly. Okay, this is great for simulations and such like that. Okay, now you don't want to use a standard encryption algorithm for passwords. Okay, because they are very, very fast. Okay, hence you can have those dictionary attacks. Okay, so what we use is adaptive one-way functions. Okay, adaptive one-way functions compute a one-way irreversible transform. So hey, but don't we have that with secure hashes? Yes, but each function allows configuration of a work factor, making so we can make it harder to compute these things. Remember, when we check a password, we only check it at login. We're not using it for every piece of data that goes back and forth. For that, we can use very quick algorithms, and that's built in with HTTPS in your browser. This is happening once. We want this to be hard. Okay? So, there's a whole different set of algorithms that are used. We don't use the same encryption algorithms that you may have learned about in a security class. Okay, we don't use the algorithms that are used for public key cryptography. We don't use the ones that are used for symmetric keys, things that are used after sessions have been established, like in HTTPS. We don't use those algorithms. There's a special class of algorithms. They actually have competitions and have had competitions for password hashing. Okay, Argon 2 is the winner of the most recent of these competitions, and it should be considered your first choice for new applications. Okay. Password-based keying, I forgot what all the acronyms stand for, is a federal government certification or certified approach, okay, for password hashing. Okay, scrypt is good for resisting any and all hardware accelerated attacks. Okay, when you can't get these other two to go, bcrypt. Okay, use it where you can't get any of these others working. Okay, this was once the leader for the longest time. Okay, all of these are better than any other approach. Any of these is better than any other approach. Okay, any other approach to hash the passwords not on this list is not recommended. Okay, now why different algorithms? Some may not be available for your platform. Many are based on C and C++ libraries. Okay, so that means getting down, okay, because yes, these have to run fast and stuff like that. There is a JavaScript only version of bcrypt called bcryptjs, okay, that you can use if you can't get like Argon 2 to install. Okay, in this class, this is what we're actually going to use because I don't want any installation headaches for anybody. We have enough things to worry about. Okay, so what is basic password processing on the server? Okay, so I'm going to say it once again. We never, ever, ever store unencrypted passwords on a server. Okay, you should not use just any encryption algorithm. Okay, most encryption algorithms are designed to be fast and secure. Being fast with password encryption leaves us the system open to dictionary attacks. Okay, you've got to use one of those password algorithms on the previous page. In this class, we're going to use bcryptjs. It's about 30% slower than a C, C++ implementation. People have actually measured it, so that's not too bad for us. And okay. Now, how will we use it? Fairly simple. npm install bcrypt. Oh, this is on the node side. Yes, this is on the node side. We're doing this for the server. Yes, servers hold the passwords. When somebody sends their password to the server, it has to do this algorithm. and the server will never ever store the password sent to it in the clear. Okay, so we bring in bcrypt, we generate the salt, we use the salt with the hash, okay, and boom, we get our password. Okay, and there's a function you can do this in one step too. Just look at the documentation. To verify, we bring in bcrypt, okay, JS. Notice bcryptjs. Okay, this is all JavaScript. So I got these hashes from running the previous code at a particular point in time. Okay, every time you run it, because it uses a random salt, this stuff will all look different. Okay. Now, what you do is run bcrypt compare, okay, my password thing to the hash, okay, and it will compute whether the newly sent password matches when hashed appropriately with the salt and such, and the hash are the same. Okay, that's simple. Okay, this takes some work. Okay, on the computer side. Our side, not too much. There are just definite procedures that we should use to do these kind of things. Now, that's the start though. We're going to be developing web servers, okay? We need to start with some user data. We don't have any users yet. So we're going to create fake user data, okay, with fake passwords and any other information your application might need about them, okay? There are tools to generate that kind of fake data, okay? I use this tool to generate some of the fake data that I will hand to you for the class, okay? Fake users, passwords, we're going to put these on our, wait a second, I thought you said net ID, first name, last name, email. Oh, here's some fake data generated by this service. I can get it to put student ID formats in the exact format for my university. Okay. Email, password, fake looking emails, and such like that. None of this is real. Okay. Professor, yeah. I thought you said not to use passwords in the clear. Well, you know, it's just, no, there's no exceptions. This is the student data. This is the data with their fake student, fake password. We never keep this on the server. What do? Okay. If we're gonna put this on a server, we have to remove all those password fields and add a field to hold the secure hash. Okay. So that'll be a coding assignment, but afterwards I'll have something like this. Okay. So I have my fake students. Okay. I have their email, but now I have the secure password hash using the appropriate algorithm. This is appropriate to put on your server, up with your server, when you start testing it. Okay. Not the other file. Now you need to have the other file on your computer for testing because you're going to try logging in as users, right? So you need the password in the clear. We never put that up on the server. Okay. Why are you saying this over and over again, Professor? Because you will develop an application. Okay. A server thing. Okay. And you'll get it going. And as soon as it looks like it's kind of working a bit, somebody in management will say, okay, that's it, ship it. Okay. You do not get to go back and put security in. You have to put at least a minimum level of security from the start. And that minimum level is we will never, ever, ever have cleared passwords stored on the server, even in development. Okay, no exceptions.